Today we want to talk about exponential functions. An exponential function looks like f of x equal to a number times b to power x. B is called base. It has to be bigger than 0 and not equal to 1. A few examples of exponential functions. Let's do the example 1. Mark all functions that are exponential. This one is an exponential function. Why? Because base is a number and a variable to a power variable. Here it's an exponential function and the base is 1/2 to power x. This one is not an exponential function because the base is not a number, it has variables in it. So this one is incorrect. Before continuing, I want to discuss briefly what Euler's number is. We usually show Euler number with, we always show Euler number with the letter E, and that's reserved, like how pi is reserved for 3.14 and goes on forever. Euler number is 2.7 and goes on forever. And this is actually a natural base for exponential functions, and we discuss it later as we go. Now, for example 2, I would like to do a few exponents and then use how this works to graph a couple of exponential functions. Let's say, what is 3 to power 5? That means that 3 times 3 times 3 times 3 times 3, 5 times, and that's these two multiplied together is 9. This 3 are 27, then it's 81. Then it's 81 times 3, which is 243. Now, what is 1/3 to power 5? That would be 1 to power 5 divided by 3 to power 5, and that is 1/243. Now, what's 3 to power negative 5? That is, again, 1/3 to power 5, and that's the same thing as this problem. What's 9 to power 5/2? So what we so far have done is the power positive, we've done power negative, we've done base that is less than 1. Now it's base bigger than 1, and power is not an integer. Now, this one, I can do 9 to power 1/2, then to power 5. 9 to power 1/2 becomes 3, because 1/2 means the second root of 9, and then to power 5 makes it 243. Now, what is 27 to power 5/3? Again, 27 to power 1/3 to power 5, which is 27 is 2 times 2 times 2, that's 2 to power 3, 2 to power 3 to power 1/3, so this is 2 to power 3 to power 1/3, makes it, 3 to power 3 to power 1/3 makes it 3 to power 5, which is 243. Now let's try to graph, first of all, y equal to 1/2 to power x, and then y equal to 2 to power x. And so I need a few points. Let's try to plug in, let's say, x value -1, 0, 1, and then maybe 2. So, and then y value for -1, 1/2 to power -1 is 2. 1/2 to power 0 is 1. 1/2 to power 1 is 1/2. 1/2 to power 2 is 0.25. And I can choose another one over here, -2, -2. 1/2 to power -2 is 1/2 to power -1 to power 2, which is 2 to power 2, which is 4. So now I'm graphing it. At negative 2 we have 4 up here, then we have 2, then we have at 0 we have 1, then at 1 we have 1 is approximately right here. At 1 we have 1, and we have 0.5. At 1 we have 0.5, and then at 2 we have 0.25. So it looks like this. What we observe is that as number x value grows, the y value gets smaller and smaller, positive number, and therefore x y equal to 0 is an asymptote. But the asymptote that goes to the right side, it's not an asymptote on the left side. On the left side, it just grows. It's as we approach the negative infinity, the left side grows to positive infinity. Now let's do the same thing for y equal to 2x. So x and y, and I can plug in negative 2 and I get 0.25. I can plug in negative 1 and I get 0.5. I can plug in 0 and I get 1. And 1 I get 2. At 2 I get 4. And so at 4 up here, at 2 down here, at 0 down here, at negative 1, it's 0.25, and then even smaller. So it looks like that. This one, as x grows, y grows, and then other things to notice, there's a y asymptote. This time y asymptote is to the left. What are the differences? When base is less than 1, positive number less than 1, it actually decays. The graph decays to 0, and when the base is bigger than 1, the graph grows. And both functions have an asymptote. For this one, asymptote is on the right. For that one, asymptote is to the left. So it has to do with the relationship of the two also. So what happens is that I can write 1/2 to power x, or I can write 2 to power x. And this shows that the two graphs actually are a mirror image of each other over y-axis, and that's something to observe. Other things to observe: whenever I'm plugging in 0, I get the y-intercept for both of these, and if there is no other function number multiplying the exponential itself, this is going to be 1. And the next thing we want to cover is graphing the exponential functions that are coming from the exponential functions that are some transformation of the parent function b to power x.